All right, so this is the second portion of section 4.5. Last time we did the first couple problems from this section, but since it's pretty long and there are a lot of different problems in this particular section, we split it into 2 days. So if you've not already watched the first part of this section 4.5 video, I do recommend that you go do that. But here are some more examples. So we're starting off with example 4. It says an 8-foot tall fence runs parallel to the side of a house 3 feet away. What is the length of the shortest ladder that clears the fence and reaches the house? All right, so let's draw a picture here. That's how we always start. So I have a house here, and running parallel to it is a fence, and the fence is 8 feet tall. The house and the fence are 3 feet away from each other. And then I have a ladder that I want to touch the house and clear the fence. And so I'm going to call this is the ladder, and I'm going to say that it has length L. I'm going to call the height of the house B, and I'm going to call the distance between the fence and the start of the ladder X. So this is the picture that we are dealing with. And I want to make a note that we actually have 2 different triangles here. So we have our big triangle and we have our small triangle. So, oh, whoops, sorry about that. So our big triangle has length here, x plus 3, hypotenuse L, and length here, B, and this is our angle. And then our small triangle has adjacent side x, height 8, since that is our fence, and an unknown hypotenuse. But these 2 triangles are similar. They are similar triangles. That means that they have proportional relationships with their sides, which we will use here in a second. So how can I relate all of my variables together, and what is the thing that I want to optimize? Well, I'm trying to minimize the length of the ladder. So how do I relate the length of the ladder and our distance x and b here? Well, I can use the Pythagorean theorem. So I know that L squared is equal to x plus 3 squared plus b squared. But this is in terms of 2 variables, right? And I don't want that. I want this in terms of only x or only b. So I'm going to use my proportionality here in order to solve for one of the variables in terms of the other. So because these are similar triangles, I know that 8 over x, the proportions of the sides of the smaller triangle, is equal to b over x plus 3. If I cross multiply, I get bx is equal to 8 times x plus 3. And dividing through by by x gives me b is equal to 8 times x plus 3 divided by x. So this is b in terms of x, and I can now replace that in my equation for L squared here. So I will have x plus 3 squared plus b squared. That's 8 times x plus 3 over x squared. And let's factor out this multiply out this squared term now. So I have x plus 3 squared still. If I square every term in my 8 times x plus 3 over x squared, I get 64 times x plus 3 squared divided by x squared. And from this, I can factor out an x plus 3 squared. Whoops. So if I factor out an x plus 3 squared, I'll be left with 1 plus 64 over x squared. So this is L squared, but I'm not looking for L squared, am I? I'm looking for L. Well, I'm going to use a trick here that is definitely a tricky trick, but it says the following. Because L has to be a positive distance, L squared and L have the same local extrema. let me write that down. L and L squared have the same local extrema. Since L has to be positive. If you're curious about why this is true, feel free to come to the Zoom meeting. I'd be happy to explain. So I just want to find, so here instead of L squared, I'm just going to replace it with an L. So I know that L is equal to x plus 3 squared times 1 plus 64 over x squared. That I know is true. Okay, so now since I want to try to optimize L, I'm going to take the derivative and set it equal to 0. So I see that L prime, I'm going to have to use the product rule here. So L prime is equal to the first, x plus 3 squared, times the derivative of the second. What's the derivative of the second? Well, that 1 disappears. We can rewrite 64 over x squared as 64 times x to the negative 2. And if we take the derivative of this, I get negative 128x to the power of negative 3, or negative 128 over x cubed. So that is the derivative of the second, negative 128 over x cubed. Over x cubed, plus the second, 1 plus 64 over x squared, times the derivative of the first, which is 2 times x plus 3. All right, and I'm trying to set this equal to 0, so I want to simplify this as much as I can. So it looks like from both of these terms, I can factor out an x plus 3. When I do that, I am left with 1x plus 3 on this first set times negative 128 over x cubed plus 2 times this 1 plus 64 over x squared. And I'm actually going to simplify this second set to 2 plus 128 over x squared. 2 plus 128 x squared over, 120, yeah, that's right. Wait, hold on. 2, what did I just write down? Sorry. I had 2 times, yeah, okay. So 2 plus 128 over x squared. There we go. Okay. So again, I want to simplify this as much as possible. So what I'm going to do from here is try to combine this x plus 3 times negative 128 over x cubed plus 2 plus 1 over 28 over x squared. I want to get these into one single fraction. And the way that I'm going to do that is I need to multiply this x plus 3 by x cubed over x cubed. Our common denominator here will be x cubed. So I'll get x cubed over x cubed. I need to multiply this 2 by x cubed over x cubed. And I need to multiply this x, 1 over 28 over x squared, by x over x. This will make it so that all of our denominators are equal to x cubed. So this will be, I still have that x plus 3 out in front, x cubed over, well, all of this will be over x cubed now, right? So I have x plus 3 minus, that 128 was already over an x cubed, so I didn't need to do anything there, plus I have x cubed times 2, so that's 2x cubed, plus 128x. Oh my gosh. Whoops. So sorry about that. I was thinking that my math looked wrong, and it does look wrong. So my apologies. I messed up some algebra here. So we do want that common denominator of x cubed, but I didn't need to multiply this guy by x cubed over x cubed because it's already over x cubed. These are being multiplied together, so sorry about that. But I did need to multiply this 2 by x cubed over x cubed and this 128 over x squared by x over x. So my apologies. All right, so we still have this x plus 3, and then I have negative 128 x plus 3 over x cubed, will all be over x cubed now, plus 2x cubed plus 128x. Okay, so if I simplify this a little bit, I will get x plus 3 times, I get negative 128x. Negative 128 times 3 is equal to 384, so I get minus 384 plus 2x cubed plus 128x over x cubed. Let's see, my 128x's cancel. I'm going to have to move down here since I'm running out of room. And I'm left with x plus 3 times negative 384 plus 2x cubed over x cubed. Whew, and that is as simplified as it can get. And again, I'm trying to solve for L prime here, so I set this equal to 0. Congrats, we almost are done with this problem. All right, so I have two things that are multiplied here that are equal to 0, so that means that each term can equal 0. So if I set x plus 3 equal to 0, I get x is equal to negative 3. But that does not make sense here. This x is a positive distance, so we throw this answer out because it does not make sense. Then I have the possibility that I have negative 384 plus 2x cubed over x cubed equal to 0. So when I have a rational function like this equal 0, I know that that means that the top has to equal 0. So I have negative 384 plus 2x cubed equals 0. This means that 2x cubed is equal to 384, or x cubed is equal to 192, which means that x is equal to 5.77. So this is my critical point, and I do not need to test the endpoints here because it does not make sense to have 0 length or infinite length. So that means that x, or the length from the fence to the bottom of the ladder, is 5.77. But that's not what I wanted to find. I wanted to find the length of the ladder, but luckily I can do that using my original function. So here I have L squared is equal to x plus 3 squared times 1 plus 64 over x squared. If I plug in x here, I get 8.77 squared times 1 plus 64 over 5.77 squared is equal to 33.2929. So if I, let's see, so this is 8.77 squared times 2.92, and this is equal to, we're almost there, 224.76. This is equal to L squared. So I get L is equal to approximately 15 feet. Yeah, I definitely should have made that space a little bit bigger, but that is L. So this is the shortest length of this ladder that clears the fence and reaches the house. Woo! How fun are these problems? I think the hardest part about this one, honestly, was the algebra. So, but we did the same thing, right? We found our constraint equation and our objective function. We had to replace one of our variables with an expression in terms of the other one so that we got it into a single variable. We did have to use the fact that L and L squared have the same local extrema. That was pretty tricky. But then from there we just solved as normal. I know that some of these are hard because they are word problems and those are challenging for a lot of us. So I do highly, highly recommend coming to the Zoom meetings, asking questions, and just practicing, because practice makes progress when it comes to these kinds of problems. Okay, let's move on to the next example. This one is not nearly as challenging in my opinion. So we have a water storage tank in a small community is built in the shape of a circular cylinder with a capacity of 32,000 cubic feet. The interior walls and the floor of the tank must be cleaned and treated annually. Labor costs for cleaning the wall are twice as high per square foot as the cost to clean the floor. Find the radius and the height of the tank that minimizes the cleaning cost. Alright, so we have a cylindrical water tank here. We don't know the radius or the height because that's what we're trying to solve for. But I do know that the volume is 32,000 cubic feet. So we have our radius here and our height. So we want to minimize the cleaning cost, right? So our function that we are trying to minimize is cost. And here it says that the cleaning costs for the walls are twice as high per square foot as the cost to clean the floor. So I'm going to say cost is equal to wall cost plus floor cost. We're trying to minimize this. So now I just need to figure out what each of these are. So what is the, how can we express the surface area of the wall in terms of R and H? Well, if we think about what the wall is, right, it's the circumference of the circle. That's like the length of it times the height. So our wall is equal to circumference times height. And circumference is equal to 2 pi r h. And we need to note that the cleaning costs for the wall are twice as high per square foot. Okay, what about the floor? What is the surface area of the floor? Well, it's a circle, so it's just pi r squared. So our total cost is equal to the wall cost, which is 4 pi r h. Since I have 2 pi r h, and then I have to multiply it by 2 since it's twice the cost, plus pi r squared. Alright, well again, we have two variables, r and h, so I need to solve for h in terms of r. I'm going to use the fact that my cylindrical tank here has a volume of 32,000 cubic feet. So my volume is equal to base times height, which is equal to pi r squared times h, and in this case my volume is 32,000 feet. So I want to solve for h in terms of r, and in this case I can simply divide by pi r squared, and I get h is equal to 32,000 divided by pi r squared. So our cost here is equal to 4 pi r times h, which is 32,000 over pi r squared, plus pi r squared. I can simplify this a little bit. I can cancel out these pi's and one of the r's. So I'm left with, let's see, 4 times 32,000 is 128,000. So I get 128,000 over r plus pi r squared. That is the cost function. So now that I have my cost function, or my objective function, in terms of a single variable, now I can find the derivative and set it equal to 0 to find the max and the min. So I'll say c prime is equal to negative 128,000 over r squared, that's the derivative of 128,000 over r, plus 2 pi r. We don't have to use implicit differentiation here since our r is constant. And I want to set this equal to 0. So I can add this negative 128,000 over r squared to the other side to get 2 pi r equals 128,000 over r squared. If I multiply both sides by r squared, that gets rid of that fraction. So I get 2 pi r cubed equals 128,000. Dividing both sides by 2 pi gives me r cubed is equal to 128,000 divided by 2 pi. And if I find the cube root of this, I get r is equal to 27.3 feet. And now I need to solve for the height. Luckily, I have a handy-dandy expression here. So h is equal to 32,000 divided by pi r squared. R is 27.3. And this is equal to 13.7 feet. So this is the radius and the height that minimize the cleaning cost of this tank. Pretty cool, right? All right, we have 2 more examples left. You guys are doing such a great job. I know these are hard problems. So next we have a problem that says what point on a line y equals 4x plus 2 is closest to the origin? Now there is a way to do this problem using calculus, but I'm actually going to show you a way that doesn't use calculus. So let's draw a picture here. I have the line y equals 4x plus 2, looks something like this. And I want to figure out what point on the line is closest to the origin. So if I were to draw, so we'll just estimate it, right? So we'll say this point is closest to the origin. Well, if I draw a straight line from that point to the origin, I see that these 2 lines are perpendicular to each other, right? So the point on the line, 4x plus 2, that's closest to the origin, if I were to draw a line between the origin and that point, they would be perpendicular to each other. So I have my line here, 4x plus 2, and I'm going to call this point P. And what I'm going to do from here is I know that the line P, I know what the equation, we'll call this whole line, I don't know, B. So the line B, I know what its slope is. Since these 2 lines are perpendicular, my slope for this is the opposite reciprocal of the slope for y equals 4x plus 2. And this line B goes through the origin. So I know that B is equal to negative 1/4 x. And I'm trying to find the point where B, which is equal to negative 1/4 x, and 4x plus 2 intersect each other. So now I just need to solve for x. So I will add, actually, you know what, I'll subtract 4x from both sides to get negative 4.25x equals 2. So I get x is equal to, negative 0.47. That's my x value. And then to solve for y, I can plug it either into my b line here or my regular equation. So I'll say y is equal to 4x plus 2, which is 4 times negative 0.47 plus 2, which is 0.12. So the point that is closest to the origin on the line y equals 4x plus 2 is the point negative 0.47, 0.12. There is a way to do this using calculus in terms of distance. We would be using the Pythagorean theorem, but I think it's pretty cool that we can solve this problem just by using perpendicular lines. All right, we have one last problem. This is a personal favorite of mine. It says a piece of wire of length 60 is cut, and the resulting 2 pieces are formed to make a circle and a square. Where should the wire be cut to maximize the area of the square? So I have a wire here. It's got length 60, and I want to cut it somewhere and make one piece into a circle and the other piece into a square. And I know that it has total length of 60. So I want to figure out where it needs to be cut to maximize the area of the square. So let's figure out what relationships I have going on here. So if I were to cut this and make one of the pieces into a circle, that would be the circumference of the circle, right? So I have 60 is equal to the circumference of the circle, I'm going to say 2 pi r, plus the perimeter of the square, which I'm going to say is 4s. Because again, these pieces of wire will form the circumference or the perimeter of these two shapes. So I have 60 is equal to 2 pi r plus 4s. Okay, but I want only one equation, right? So let's see if I can simplify this a little bit. I know that the area of the circle is equal to pi r squared, and I know that the area of the square is equal to s squared. So this is what I actually want to maximize, is the total area. So total area, we accidentally did so this is the constraints, right? So this is, the area is what I actually want to maximize. I did it in the wrong order, but no worries. So the total area is equal to pi r squared plus s squared. And from here, I want to use the constraints that I already wrote in order to get this into a single variable. So using 60 is equal to 2 pi r plus 4s, I can solve for either r or s. So I'll solve for, let's see, I'll solve for s, I guess. If I subtract 2 pi r from both sides, I get 60 minus 2 pi r is equal to 4s. So s is equal to 15 minus 1/2 pi r. That is s. So then my total area is equal to pi r squared plus s squared, which is 15 minus 1/2 pi r squared. Okay, if I were to factor or multiply out this square term, I would get pi r squared. Actually, you know what, let's not do that because we're going to have to find the derivative anyway. So this is my total area, and this is what I'm trying to optimize, so I need to find the derivative of this and set it equal to 0. So I'll say a prime is equal to 2 pi r plus, I have to use the chain rule here, right? So I get plus 2 times 15 minus 1/2 pi r, that's the derivative of the outer function, times the derivative of the inner function, which is negative 1/2 pi. And I want this to be equal to 0. So from here, I need to solve for r. If I multiply out these last few terms, I get 2 pi r plus 2 times 15 times negative 1/2 pi is negative 15/2 pi. And then I get plus 1/4 pi squared r is equal to 0. So multiplying out that 2 gives me 2 pi r plus negative 15 pi plus 1/2 pi squared r equals 0. And remember, I'm trying to find r, so I'm going to move this 15 pi over, and I get 2 pi r plus 1/2 pi squared r is equal to 15 pi. Now I will factor out an r. I'll be left with 2 pi plus 1/2 pi squared equals 15 pi. And finally, I can solve for r is equal to 15 pi divided by 2 pi plus 1/2 pi squared. This is equal to 4.2. So we just solved for the radius of the circle. That's not where I need to cut my piece of wire though, because this is just the radius, and what I'm caring about on the piece of wire is the circumference. So if I have a radius of 4.2, my circumference is equal to 2 pi r, which in this case is 20.39. Wait, 26.39? 20.39, hold on. 2 pi times 4.2 is 26.39, sorry, 26.39. So you would need to cut the wire at 26.39 in order to maximize the area of the circle and the square. Whew. So here our objective function was the total area. I had to use the relationship of the circumference and the perimeters in order to isolate one of the variables. And then from there I found the derivative, set it equal to 0. In this case my endpoints don't matter since I need both a circle and a square. And from there we had it. Alright, really good job today, guys. I know this is a challenging lesson. Please, please, please let me know if you have any questions on this section. But again, practice makes perfect. So go do a bunch of practice on these problems, and I will see you later. Have a good day.